We use ChatGPT and other large language models every day. But have you wondered, how does it actually work? To understand what happens behind the scenes, let's start with a very simple example. We'll build a tiny language model that works on characters instead of words. The goal is simple: predict the next character from a sequence of characters. Let's consider a simple training dataset: ABCD, 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 and so on, where we already know what the prediction should be. At every step, we try to predict the next character. Unlike real LLMs, we won't use prompts or instructions, just to keep things simple. From our training data, characters like A, B, C, D, and space, we first create a vocabulary. Computers don't understand these characters directly. Their world is made of numbers. So we assign an integer to each character, which will be used for indexing. Now, a text becomes a sequence of integers. Our task is to predict the next integer and then map it back to a character. From here on, we'll call each character a token. In order to predict the next character, we need to create a model that applies on input tokens and predicts the target tokens. For every token in the dataset, the next token becomes the target. This is how the model learns what should come next. At a high level, this is how the transformation looks. Tokens are first converted into integers. Each token is then mapped to a learnable vector called an embedding. These embeddings pass through a transformer block where tokens exchange information using attention. The model then computes raw scores called logits for every possible next token. These scores are converted into probabilities. We compare them with the expected output to measure the prediction error. At its core, the model relies heavily on linear transformations, using input activations, weights, and biases to produce output activations. So, how does this training happen? It does not happen on the entire dataset at once. Instead, it happens in batches. Each batch contains multiple token sequences processed in parallel. For example, here we see a batch with 8 tokens per sequence and 4 parallel sequences. Each token is first expanded into its embedding vector. The transformer operates on these continuous vectors. At the end, we compute logits using an unembedding matrix, converting them into probabilities and then calculating the average batch loss. The model then updates its weights and biases using backpropagation. This process repeats many times. For now, let's focus on the first row of this batch for sample calculations. First, we convert tokens into embedding vectors. These embeddings are learned parameters of the model. If the embedding size is 4, each token becomes a vector of 4 numbers. We also add positional embeddings so the model knows the position of each token in the sequence. This is what the model actually sees: an 8 cross 4 matrix for just one sequence in the batch. Now let's understand the transformer block, the core of the model. The first step is normalization. Activations are normalized to keep values stable during training. Layer normalization rescales activations to have zero mean and unit variance, and then applies learned scaling and shifting parameters too. The second step is multi-head attention. Here, the tokens interact with each other to understand how they are related. This interaction is split across multiple heads, so the model can learn different types of relationships in parallel. Some heads may learn syntax, other semantics, or long range dependencies. For example, the cat sat on the couch and it slept. From this statement, the model needs to understand that it refers to the cat and not the couch. Mathematically speaking, attention aligns the embedding vectors, so related tokens point in similar directions in the vector space. The third step is the feed forward network. Here, each token is independently processed through a small neural network. This adds nonlinearity and also increases the model's expressive power. After tokens exchange information through attention, the feed forward network allows each token to further transform and refine its own representation. Together, normalization, multi-head attention, and the feed forward network form one transformer block. This block is stacked multiple times in the model in a single iteration itself. We also need to cover two important details. First is that the output of each step is added back to the original input. This is called a residual connection, and this helps preserve information. The second one is that during training, dropout randomly sets some of the activations to zero, which helps prevent overfitting of the model. After passing through all transformer blocks, activations are normalized one final time. We then compute logits using unembedding metrics. You can see now each column corresponds to a token in our vocabulary which has size 5. These logits are then converted into probabilities and we compute the loss by comparing them with the target token. We only look at the last time step because that represents the prediction for the next token after the sequence. Since the model is still untrained, it assigns higher probability to tokens 3 and 4, while the correct target token is 2. This loss acts as a penalty. The model computes gradients with respect to all parameters and adjusts weights to increase the probability of the current token. This process is called backpropagation. After training, these optimized parameters are used to generate new tokens from a given input sequence. Now, let's look at the results. For this simple dataset, the model behaves exactly as expected. If we train the same model on a dataset like the Harry Potter books, we get much richer generated text, as you can see on the screen. The output still isn't fully meaningful because this is a character level model. Humans think in words and not characters. And also, the data set is still relatively small. But even so, the model has learned basic language structure very well, be it punctuation, spacing, or dialogue patterns. Large language models are simply the same idea scaled up with more data, more parameters, and more compute. Hope this helped you understand a little bit more about how it all works.